You've thought about space your whole life. Rockets, astronauts, billions of dollars just to leave the ground for a few minutes. And at some point, maybe when you were a kid, maybe last Tuesday, a thought crossed your mind that felt almost too simple to say out loud. Why can't we just build stairs? Not a joke, an actual question. If space starts at 100 kilometers above your head, and humans have built structures over 800 meters tall, why is the gap between a really tall building and the edge of space still completely empty? Why are we still strapping people to controlled explosions when the alternative sounds like something you could draw in 30 seconds? The answer is not what you think it is. And the reason it isn't what you think tells you something genuinely strange about the universe you're standing in right now. Start with the number. Space begins officially by international agreement at 100 kilometers above sea level. That's called the Kármán line. 100 kilometers. Your brain hears that and converts it immediately. That's about the distance from one city to the next. People drive that on a Tuesday morning without thinking twice. If you could point your car straight up and just drive, you'd be in space in under an hour. So why hasn't anyone just built the road? The first answer everyone reaches for is height. The structure would be too tall. Nothing has ever been built that high. The Burj Khalifa, the tallest building on Earth, stands at 828 meters. 100 kilometers is 100,000 meters. You would need a structure roughly 120 times taller than the tallest thing humans have ever built. That feels like the answer. That feels like where the conversation ends. But it isn't, because taller isn't actually the problem. Here is where it gets strange. A building doesn't fall over because it's tall. It falls over because of the forces acting on it. Wind, its own weight, the lateral pressure that accumulates as height increases. Engineers have known for decades that with the right geometry and the right materials, you can theoretically go much higher than the Burj Khalifa. The physics of pure height on their own are not the wall. The wall is what's waiting at the top. To understand it, you need to understand what space actually is, not the concept, the physical reality. Space is not a place you arrive at, it's a condition. The condition of being beyond the atmosphere. And the atmosphere doesn't end like a cliff. It thins, gradually, continuously. The air gets less and less dense the higher you go, and by the time you reach 100 kilometers, there is almost nothing left. A near perfect vacuum. No air pressure pushing on your structure from the outside. No air resistance cushioning the forces acting on it. That matters more than you think. Every structure on Earth is built inside a pressurized envelope. The atmosphere itself is part of the engineering. It equalizes forces. It resists wind by being present everywhere equally. But a structure that extends from sea level into near vacuum is not inside one environment. It's inside two radically different environments simultaneously, with a continuous transition between them. The engineering challenge isn't just height. It's building something that works at sea level pressure and near zero pressure at the same time. Held together across 100 kilometers of shifting atmospheric conditions, temperature swings from positive 40 degrees Celsius at the base to negative 70 at the midsection, expanding and contracting with every day and night cycle. Now add the weight. A staircase to space would need to support itself. Every meter of structure above you is weight pressing down on everything below it. By the time you've stacked 100 kilometers of material, the pressure at the base isn't just enormous. It's beyond anything any material that currently exists can withstand. Steel, the backbone of every skyscraper ever built, would be crushed by its own mass long before you reach the top. Concrete would fail. Titanium would fail. The structure would collapse under itself before it ever cleared the lower atmosphere. This is not a funding problem. This is not a political problem. This is a materials problem. The strongest material humans have ever produced by tensile strength per unit of weight is carbon nanotube fiber, discovered in the early 1990s. A tube of carbon atoms arranged in a hexagonal lattice, 1 atom thick, roughly 100 times stronger than steel at a fraction of the weight. In theory, carbon nanotube cables are the only material with the specific strength high enough to support a structure reaching 100 kilometers without collapsing under its own mass. In theory, because here is where the real wall appears. The longest carbon nanotube fiber ever produced in a laboratory, as of now, is measured in centimeters, not meters, centimeters. Scientists have been trying to scale nanotube production for over 30 years. The physics of growing them at scale introduce defects, impurities, inconsistencies in the lattice structure that reduce their strength by orders of magnitude. The gap between what carbon nanotubes can do in a lab and what they can do at the scale of 100 kilometers is not an engineering gap. It is a materials science gap that has not closed in 3 decades of trying. And even if you solve the materials problem tomorrow, the structure would still be trying to kill you. Think about what a 100 kilometer tower would look like from the outside. It would be a rigid column standing on a rotating planet. The Earth spins, 1 full rotation every 24 hours. At the base, that rotation is slow enough that you barely notice it. But the higher you go, the faster the tip of your structure is moving through space, because it's tracing a much larger arc in the same amount of time. By the time you approach the upper atmosphere, the top of your staircase is experiencing forces from the Earth's rotation that would flex and torque the structure in ways that compound with every gust of upper atmosphere wind, every gravitational pull from the moon's tidal forces, every thermal expansion cycle. It would sway. The engineering term for managing that sway in a super tall structure is damping, and every super tall building on Earth has damping systems built into it. The Taipei 101 skyscraper has a 660 metric ton steel pendulum hanging inside it, specifically to counteract sway. A 100 kilometer structure would require damping at a scale that has never been engineered or even modeled successfully. Now, here is the twist that changes everything. Engineers figured this out. They looked at every one of these problems, the materials, the weight, the rotation, the atmospheric transition, and they didn't abandon the idea, they inverted it. What if instead of building up from the ground, you built down from orbit? In 1895, a Russian scientist named Konstantin Tsiolkovsky stood at the Eiffel Tower and had a thought. If you anchored a cable not to the ground but to a satellite in geostationary orbit, a satellite that stays fixed above one point on Earth because it orbits at exactly the same speed, Earth rotates and then lowered that cable down to the surface, the centrifugal force of the orbiting anchor above would keep the cable taut permanently. A cable under tension from above rather than compression from below. No structure bearing weight on itself, just a tether. He called it a space tower. Everyone who came after him called it a space elevator. The physics work. The mathematics are sound. The concept has been studied seriously by NASA, by the Japan Aerospace Exploration Agency, by private engineering firms. In 2000, NASA commissioned a detailed study. The conclusion was unambiguous. The concept is physically valid. The cable under tension from a geostationary anchor could theoretically support a climber, a mechanical platform that grips the cable and ascends it, carrying cargo and eventually passengers, powered by microwave energy beamed from the ground. No rockets, no fuel. Just a platform climbing a cable at a few hundred kilometers per hour, reaching orbit in roughly a week. The cost per kilogram to reach orbit by rocket today sits somewhere between $2,000 and $10,000 depending on the launch system. Estimates for a mature space elevator put that number below $100 per kilogram. The economics aren't incremental, they're civilizational. And the only thing standing between that future and right now is the cable. Carbon nanotube fiber, still measured in centimeters. So when you ask why we haven't built stairs to space, the real answer isn't that nobody tried. The real answer is that the people who thought hardest about it realized stairs were the wrong shape. A rigid structure pushing up from the ground collapses under itself, but a cable hanging down from orbit stays taut under its own tension. The solution to the problem isn't taller, it's upside down. Right now, somewhere in a materials science laboratory, someone is trying to grow a carbon nanotube fiber longer than the ones grown yesterday. The increment is probably microscopic. The goal is a cable 100,000 kilometers long. The stairs were never going to work, but the elevator might. And the next time you look up at the sky and think about how impossibly far away space seems, remember, the plan that physicists actually believe could get you there doesn't start on the ground. It starts in orbit, and it reaches down to find you.